Welcome to The Explainer. Today, we're diving into something absolutely wild. We're looking at a fascinating new study on autonomous robot-based neuroregistration. Basically, we're talking about a breakthrough in medical engineering that makes brain surgery significantly faster, infinitely more precise, and, this is the crazy part, entirely hands-free during the crucial setup phase. So, if you've ever wondered how advanced robotics are literally transforming the modern operating room, you are in for a treat.
Okay, let's just jump right into the fundamental problem here. Picture this. A patient is lying on an operating table. The surgeon knows there's a microscopic tumor hiding somewhere inside their skull. But how does a robotic arm, which is essentially a blind machine, know exactly where that target is in physical space, without a human making a potentially catastrophic miscalculation?
The secret sauce here is a concept called neuroregistration. You can think of it like a hyper-advanced GPS system. It's the absolutely crucial process of taking a static 3D medical map, like a CT scan, and perfectly aligning it with the real, physical patient on the table. When this mapping is perfect, a surgical tool can be tracked in real time, letting the robot navigate the brain with absolute certainty.
To really grasp this massive challenge, just look at the disconnect here. On one side, we have the static medical image space, the digital realm of the CT scan, and on the other, we have the real patient space, featuring the physical surgical robot and the actual patient. Our goal today is to understand exactly how researchers bridge the gap between these two completely disconnected worlds, all without relying on a human to manually play traffic cop for the robot.
To make this hands-off mapping a reality, the researchers broke the whole journey down into 3 highly choreographed steps. First, medical imaging to create the initial map. Second, initial localization to point the robot in the right general direction. And third, precise localization, where the robot autonomously hunts down the exact coordinates.
Section 1. Mapping the human brain. The phantom's journey begins.
We're going to follow the chronological journey of a skull phantom, which acts as our stand-in for a real patient, to see exactly how this breakthrough algorithm works from start to finish. It all starts right here in the medical image space. Our skull phantom is securely placed inside a standard CT scanner, specifically in the head-first supine pose, meaning it's lying on its back, head pointing toward the machine. The scanner grabs incredibly high-resolution slices of the skull that are just 0.625 millimeters thick, literally paper thin, and that gives us our foundational 3D map.
Next up, those raw images are loaded into specialized neuronavigation software. See those tiny red reference points on the 3D model? Those are called fiducial markers. Researchers manually measure the exact coordinates of these markers alongside the target tumor region, which establishes our digital target coordinates.
Section 2. Meet the 6D PKM robot, engineering the solution.
Now that we have our perfect digital map, let's transition into the physical world and meet the star of the show. This is the 6 degrees of freedom parallel kinematic mechanism, or 6D PKM for short. What's brilliant here is seeing the whole operating ecosystem at work. You've got the physical surgical robot suspended right over the skull phantom, seamlessly synced up with the real-time tracking monitor on the right.
But before we see it move, take a second to appreciate these hardware specs. It's a compact, portable setup, but it can push with a payload of 200 newtons, which is roughly 45 pounds of force. And the precision? We are talking an absolute accuracy of 60 micrometers. To put that into perspective, 60 micrometers is roughly the width of a single human hair. Add a 5-megapixel high-res camera into the mix, and you've got an incredibly capable surgical assistant.
Section 3. From images to reality. Autonomous registration in action.
Now here is the real magic, getting this hyper-precise robot to find the patient and register those coordinates entirely on its own, without a human physically guiding it. This brings us to the initial localization phase. The phantom is clamped in, and the robot gets a very basic, coarse estimate of the layout. It just needs a basic orientation, like head-first supine, and a rough guess of one marker's location. Using just that tiny bit of input, the algorithm computes a rough path to get the camera into the right neighborhood.
And that elegantly drops us right into precise localization. Check out this incredible robot vision perspective. Once it's in the general area, the autonomous navigation algorithm completely takes over. It hunts down each marker, perfectly matching a digital contour to the physical size of the marker, and crunches the exact 3D coordinates on the fly based on the camera's fixed position. It does this for all 4 markers, one by one, entirely hands-free.
Now you might be asking, why is this such a big deal? Well, compare this new autonomous system to the old-school manual methods, and the benefits are just staggering. Traditional methods rely heavily on line-of-sight tracking or having human operators physically touch points on the patient. That introduces human error and eats up incredibly valuable time in the operating room. This autonomous method, it's totally touch-free, it uses automated contour matching, making it lightning fast while hitting sub-millimeter precision. It's a real game changer.
Section 4. Pinpoint accuracy and results.
Theory is great, right? But it's absolutely nothing without hard proof. So let's look at the numbers and see how this robot actually performed. Based on the medical scans from Step 1, the team generated these exact microscopic coordinate targets. These match up to 4 distinct tiny entry points on the skull phantom. The ultimate test of the system is whether the surgical tool can autonomously hit these exact spots based purely on the math it just calculated.
Well, look at this. It absolutely nailed it. In these results, we're watching the robot physically execute its plan, and you can see the 2.5mm surgical needle hitting those 4mm markers dead center.
Actually, scratch that. It gets even better. Tapping a surface marker is one thing, but threading a needle is a whole different ballgame. Here, the robot smoothly slides that 2.5mm needle straight into microscopic 5mm and 4mm target holes drilled right into the skull. There is literally zero room for error here, and the machine executed it flawlessly.
The data really speaks for itself here. As the study concludes, the target registration error, which is the ultimate metric for success in these procedures, proved the robot achieved sub-millimeter accuracy, completely hands-free. It mapped the coordinates, navigated the space, and executed the approach with an accuracy of less than 1 millimeter across a bunch of different patient poses.
So, as we wrap up this explainer, I want to leave you with this final thought to ponder. If we can fundamentally trust algorithms and cameras to autonomously map the incredibly delicate landscape of the human brain with sub-millimeter accuracy, what's next? What other high-stakes, insanely complex surgical tasks are we finally ready to just hand over entirely to machines? The future of robotic healthcare isn't a sci-fi movie anymore. It's already here, and it's precise down to the width of a human hair. Thanks so much for joining me on this deep dive, and keep questioning the incredible science shaping our world.